Hi everyone, welcome back. My name is Souvik and I contribute to Malin. In the previous lecture, we talked about the limitations of on-chain compute, why we need off-chain compute, and how rollups can help us create a feasible on-chain job matching marketplace. In this lecture, we are going to explore the next big piece of the off-chain compute puzzle, coprocessors. We'll go over what they are, why do we even need them, and how did they work. So without further ado, let's dive in. So first things first, what exactly are coprocessors? Just like in the case of rollups, coprocessors are a different approach to off-chain computing. But instead of scaling transactions, they focus on scaling computation. I like to think of them as GPUs for blockchains. Just like GPUs help a CPU handle heavy graphics or AI workloads, similarly, a coprocessor supplements the blockchain's limited compute environment and helps it perform more compute-intensive tasks. But there are trade-offs as well. Coprocessors don't maintain any state. A common pattern you might come across while working with coprocessors would look like this. You send them a compute task, they crunch the numbers off chain, and finally, they return a result along with a cryptographic proof. You can find various types of coprocessors nowadays: ZK based, TE based, MPC based, and even FHE based ones. For example, Marlin's Oyster is a TE based coprocessor, while Brevis is a ZK based coprocessor. We'll discuss these types in more detail in the upcoming lectures. You can also think of coprocessors as network cards for blockchains. They add extra capabilities and unlock things that L1s or rollups cannot do. They are perfect for tasks that need speed, privacy, or access to the internet to fetch historic data via APIs or custom logic, like AI inference, complex data analysis, or privacy preserving computation. They can be upgraded independently and are easy to customize for specific needs. They also offer cryptographic guarantees and handle sensitive data without exposing it on chain. But of course, they're not perfect. Some coprocessors, especially the more advanced ones, can be pretty expensive to run. Moreover, in their native form, they don't maintain state, and setting them up requires specialized technical knowledge. Now that we know what coprocessors are, let's look at how they actually work behind the scenes. The architecture of coprocessors generally involves four key components. The first component is the relay contracts. They serve as bridges between on-chain and off-chain environments. Relay contracts live on-chain and act as messengers. They forward compute requests to the coprocessor and later record the verified results. The second component that we have is the off-chain coprocessor nodes. In simple terms, they are just specialized hardware units that perform the actual computations securely away from the main chain. The third component is the verification mechanism. This comes into play after the computational task is done. The node produces a cryptographic proof or an attestation to prove the correctness of the off-chain computation. The fourth and the final step is the result submission. The outputs of the task at hand, along with the proof, are sent back to the main chain. The proofs are then verified on chain to verify their correctness. Now that we have verified that the outputs are correct, the relay contract can now trigger a callback to send this result to the application contract that requested this off-chain computation. This architecture effectively separates concerns while maintaining cryptographic security, allowing for powerful off-chain computation that remains trustless. Now, let's bring this home with our decentralized job marketplace example. Say we wanted to add AI-powered resume parsing to our job marketplace so that we can match jobs more effectively. Running something like this on an L1 or even an L2 would be crazy expensive and impractical. But with a coprocessor like Marlin's Oyster, we can offload this AI task securely. It lets us process unstructured resume data, keep personal information private, verify that the AI decisions are fair using proofs, and even upgrade our AI models over time. This is a great example of how coprocessors enable features that are just not possible with regular L1 or L2 solutions. Now that we have seen both rollups and coprocessors in action, how do they compare? Well, both help take work off the main chain, but they do it very differently. Rollups are like mini blockchains. They batch and compress a ton of transactions and then post the data or proofs back to L1. Coprocessors, on the other hand, are more like off-chain general-purpose virtual machines. They execute tasks, return results, and provide proofs, but they don't maintain any persistent state. One way to think about it is if rollups are about scaling throughput, coprocessors are about unlocking new compute capabilities. They aren't competing technologies, they are complementary. Do you see a use case that can leverage both of these approaches? If so, you might be onto something. Thank you for tuning in. In today's lecture, we covered what coprocessors are, how they work, and how they differ from rollups. We also saw how Marlin's Oyster fits into this ecosystem as a TE-based coprocessor that enables scalable off-chain computation. In the next lecture, we'll dive deeper into different types of coprocessors, how they work to enable secure off-chain computation, and understand the trade-offs between them.